Well, here are the answers to the quiz on reflection and refraction of light. In this question, it's a converging lens, which means it's a convex lens. The object distance is 15 millimeter. Image is 4 millimeter behind, which means it's a real image. And you got to find the focal length of the lens. So DO is 15 millimeter, DI is 4 millimeter. It's a real image. You got to find the focal length. Use the law of distances. 1 by F is 1 by DO plus 1 by DI, which can be rearranged as product by sum is equal to the focal length. And on substitution, get 3.2 millimeter. In the second one, the object is placed 40 centimeters in front of a 20 centimeter focal length converging lens. How far is the image? Okay, direct question. Again, use 1 by F is 1 by DO plus 1 by DI. And F is positive 20. Why positive? Because it's a converging lens. Has a real focus. DO is given. You got to find DI. When you rearrange, this is how we get DI. DO minus F by DOF. It's 1 by DI. So DI is DOF by DO minus F, which gives 40 times 20 by 40 minus 20, which is 20, of course. And so that gives 40 centimeter. And in this question, index of refraction is given. Find the critical angle. Direct. N is 1 by sine C. Refractive index is 1 by sine C. So sine C is 1 by N. And then take the sine inverse of 0.67, which gives 42 degrees. Number 4, object is placed 30 centimeters in front of a diverging lens. So now it's a concave lens with focal length 10 centimeter. Okay, so now you got to take the 10 as negative 10 because it's a diverging lens. And you have to find the magnification. So first we have to find DI from this equation. Once again, DI is DOF by DO minus F. And very carefully on substituting that. So DI is negative 300 by 40, which is negative 30 by 4. And magnification is negative of DI by DO. So now we're going to get two negatives. And that's 30 by 120, which is 0.25. Number 5, the object is 5.7 centimeters from a concave mirror now. The image is 4.7 centimeter tall and 10 centimeters from the mirror. So object distance is given. You have to find how tall the object is. There are two formulas for magnification. Put both of them together and rearrange to find the height of the object. Because you have the height of the image, you have the distance of the image and distance of the object. On rearranging and calculating, we get 2.7 centimeters. A person's face is 30 centimeters in front of a concave shaving mirror. So that is DO. Image is an erect image. Now that means the upright image means it is a virtual image because only the virtual image is upright. And for the virtual image, magnification is taken as positive. So it's 1.5. Erect image is virtual. Okay. M is positive for a virtual image. That's the formula for magnification. 1.5 is negative DI by 30, which gives us That's a mistake. It should be DI. So we get DI as negative 45. And then focal length as before. Product by sum. Okay, now I'm going to change this to DI. Yes, and 90 centimeters is the focal length. 7. This is a plano convex lens. One side is plane. That means the radius of curvature is infinity. And it has a focal length 40 centimeter. What is the radius of curvature of the other surface? Now the lens maker's equation, 1 by f is n minus 1, 1 by r1 plus 1 by r2. F is 40, the refractive index is 1.65. Now 1 by infinity is 0 for the plane surface. And on calculation, R2 is 0.65 times 40, which is 26 centimeters. And in this question, the diver, at what angle must he shine a beam of light for a person on a distant bank to see it? You see, it should be at the critical angle. Sine C is 1 by n, so 1 by 1.33, and when you find the critical angle, you get 49 degrees. So he must shine it at 49 degrees. And here in the 9th one, laser beam strikes a plane's reflecting surface with an angle of incidence 52. What is the angle between the incident ray and the reflected ray? That's really simple, because the angle of reflection will also be 52 degrees. So between the rays, the angle will be 104 degrees, and the multiple choice answer is obviously wrong. It is supposed to be 104 degrees. 10. Object is 6 centimeter tall, that is HO, and in front of a diverging lens. Okay, and you got to find the focal length. So you have the height of the object and the height of the image. Magnification has two formulas. And how do we know the image is virtual? Because a diverging lens only produces a virtual image, and therefore M is positive. Put it back into this. Calculate DO. Has 100 and negative 180. Can't be negative. I'm sorry. Let me go back and correct it. That is a mistake. You know why? Because the image is virtual, so DI must be negative. So notice that two negatives here make it a positive. And therefore I had to change the sign. I'm really sorry for overlooking that fact. And therefore, when that correction is made, wait a minute. Well, obviously there is a problem here too. Oh, I just had one extra 0 here which I've removed. You know, so it was, instead of 6, I had written it as 60 again. And so when I change that, I get it as negative 13 centimeter. Well, in the next question, it's a concave spherical mirror having a focal length of 20 centimeter. An object is placed 10 centimeter in front of the mirror on the mirror's axis. Where is the image? Direct. Concave mirror has a positive focal length, so it's plus 20. DO is 10. You have to find DI. Direct question where you rearrange and you substitute for D, O and F, and you get negative 20 centimeters, showing that it's behind the mirror. 12. Why am I getting in that? Okay, in the 12th question, the object is placed at a distance of 40 centimeter from a thin lens. If a virtual image forms at a distance of 50, what is the focal length? Again, DO is given. It's a virtual image, so it's negative 50. If it's a virtual image, it's a negative 50. And you have to find F. It's product by sum equal to focal length, but when you substitute, you have to substitute DI as negative. And on doing that, you get it as 200 centimeter. How far are you from your image? When you stand 0.75 meter in front of a vertical plane mirror, of course you are 1.5 meters away, because the image is as much behind the mirror as you are in front. So the distance between you and the image is 1.5 meter. Here an object is placed 60 centimeter from a converging lens. Then the object is moved 40 centimeter from the lens. Actually, the object is moved closer to the lens, because that's when the image will move further away. So you have two cases, and in the first case take DI as x, second case it's x plus 10, because it moved away. And we get to find the focal length using product by sum. And in this case, that is going to give us 60x by 60 plus x, and there are two sets, so the next one is going to give 40 times x plus 10 divided by 40 plus x plus 10. Now it's a matter of rearranging this, cross multiplying, and when that is done carefully, you're going to get a quadratic equation. You need to carefully look at how the cross multiplication is done. If the video is running too fast, please pause it and look at it. Rearrange, bring all the terms to one side. You have 60 and 40, so that makes it 20. And then you have x is 2800 and 3000, so that's 200. And once you get the quadratic equation, solve it using minus b plus or minus square root b squared minus 4ac by 2a. And it's not 2 times 10, it's 2 times 1 here. I need to change that. So when I do that, I get 20 centimeters. Here it's a simple case of applying Snell's law. N1 sine theta I is equal to N2 sine theta R. Substitute the values and calculate. You get N2 as 1.36. Thank you. Okay, in question 16, there is red and blue light incident on a prism, and you have to find the angle between the two emerging beams of light. Basically, you have to find the angle of emergence for both and find the difference between the two. Let me show you the whole solution and then try to explain it. Now, since the ray is parallel to one of the sides, from the geometry of this diagram, this is 20 degrees. This is 70, and the total angle here is 90, and therefore this must be 20 degrees. Now, knowing that it's 20, N1 sine theta 1 is N2 sine theta 2. So 1 sine 20 is 1.530 sine theta 2, from which you find theta 2. And then use theta 2 plus theta 3 is equal to the angle of the prism, from which you get theta 3. And once again, apply Snell's law at this point when you would get theta 4. Now do the same exact procedure for the other color with a different refractive index. So for 1.525, do the same thing. Find theta 2, then find theta 3, and finally theta 4. And you see that the final angles are slightly different. So find the difference between them, and that will be the angle between the two emerging beams of light, which is 0.27 degrees. In this question 17, a prism has a vertex angle of 60 degrees, refractive index 1.52. What is the minimum angle of incidence measured away from the vertex for a ray of light to emerge from the other side of the prism? So that's the prism here. Light just emerges because it talks of the minimum angle. So we're trying to find this angle. Now theta 1, theta 4, and inside you have theta 2 and theta 3. Theta 4 is 90 degrees. From the diagram it's very clear. If it just emerges, then theta 4 is 90 degrees. That's N1, and you can apply Snell's law at the second point. And we know theta 4. We know N1 and N2, so you can find theta 3. So theta 3 is 41.14 degrees. Now theta 2 plus theta 3 is A, from which you can find theta 2. (18.86 degrees). And then I apply Snell's law at the first phase. To find theta 1. So you get 29.4 degrees. In this last question, you have to project an image of an object 4 times the actual size. Since you're projecting it, it's a real image, and for a real image, magnification is negative. The focal length is given. But we know that magnification is negative di by do. Now from here you can get a relation between di and do. So di is 4 times do, and I've substituted into the length equation. We are using 4 do for di. And when you simplify that, we're going to get do. Cross multiply and rearrange, you get do as 25 centimeter. So that's it, 18 questions on reflection of light.